So I've just started the recording, so welcome to week 4, everyone. This tutorial is about vectors today, okay? So it's like an algebra tutorial. And it's got chapter 2, the questions from chapter 2 in its listings. So let me have a quick look at that. Now, the questions in chapter 2 are mostly about operations. So let me share my screen. So there's the dot product, there's the projection of vectors, there's the Karosa product, and then a bit later there's the scalar triple product. So all these different operations. So let's have a look at some basic questions and we can move through them. Hang on, let me go back. Sorry, I'll make you dizzy. Come back. Sorry, gone too far. Here we go. Oh, so dizzy. All right. So the first thing we're going to look at in this tutorial is the dot product. Okay, and I'm going to start with question 6. So use the dot product to prove that the diagonals of a square intersect at right angles. Now, why is this an important question? Well, one of the reasons is that it's like a proof type of question. You probably look at that question and go, well, that's obvious, but how can you do it using the dot product? So that's the first question I'll look at in today's tutorial. So feel free to fire up the chat. Let me know what you're thinking in that chat, and I can share my, hang on, I'll share my document camera with you. Okay, so this is question 6 now. And I'm using new pens today, Sharpie pens. Hopefully they're okay. So the question asks us to consider a square. So here's my square, right? And I'm going to label the corners. And what they're going to ask us to do is to show that these diagonals intersect at a right angle. All right, Ning Xiao, good question. It's question 6 from page 73. Question 6, page 73. All right, so we want to show that there's a right angle here. So in the chat, can anyone tell me, using vectors, what are we trying to show here using the dot product? Can anybody put it in the chat and tell me what we're trying to do? The dot product is 0. Okay, so let's say we have the vector AC and the vector DB. If we can show that this dot product is 0, then we know that the angle there is going to be 90 degrees. Yeah? Oh, AC, yeah. Thank you. So AC, DB. All right, let me fix that up. Okay, so we're going to show that hopefully this dot product equals 0. Okay, so what I'm going to do, you can do this a bunch of different ways. I'm going to look at the vector AC and the vector DB and try to express them in terms of the sides, the vectors forming the sides of this square, right? Okay, so these little dot dashes just mean that the lengths are the same. All right, so we have the following, right? If I look at AC, so the vector from A to C, I can write that as the vector from A to D plus the vector from D to C. Yeah, thank you, Sartik. It's like you're reading my mind. That's awesome. Okay. And now let's look at the vector dB. Okay. The vector dB. Well, that's just the vector dA plus the vector AB. So this is just the triangle rule of addition. Okay. So what I'm going to do up here, I'm just going to write these in terms of these things. Okay, so I'm going to try to write this in terms of this, just because it's going to simplify some of our calculations. So the vector AD is the negative of the vector dA. And the vector DC, that is parallel and the same length to the vector AB. So I can write it like this. Okay? So now, when we do our dot product, we can use these things, and a whole lot of cancellation is going to come into effect. Okay, so that's going to be negative dA plus AB dotted with dA plus AB. And now we're just going to expand it like we would normally. Okay, so if I have a vector dotted with itself, it's just the square of the length of that vector. Okay, so that dotted with that dotted with that. That dotted with that dotted with that. So that dotted with that is the square of the length. Okay, so now hopefully you can see this cancels with this because the order doesn't matter with the dot product. And this, well, the length of DA is the same as the length of AB because it's a square, right? So we get 0. So we can just note over there, because it's a square, these two things are equal. So let's make our conclusion. Hence, diagonals intersect at right angles. That's it. Okay, now I've seen some other tutors solve this where instead of labeling the points at the corners, they just label the vectors and do that. That's fine, nothing wrong with that. That's another good way of doing it. Okay. All right, any questions, any comments? The difficult thing usually with these kinds of proofy questions is where to start. And you can see in my solution, I've drawn a picture. Pictures are so important in problem solving. They can just really help you out and help you think and visualize a problem. Okay? All right. So let's go back and have a, hang on, I'll leave that there. Let's go back and have another look at, say, question 10. So I'm just going to pop up the PDF. Okay, so hi Karen, welcome. I'm going to look at number 10 because this is a classic kind of problem. So find the shortest distances between this point and this line with this equation. Okay, so believe it or not, the key idea with this kind of problem is Pythagoras's theorem. Right angled triangles or if maybe if you're in Asia, you call it Hertz theorem, right? That's the key thing, the key idea with this, and vector projection. So we know a point on the line, and we know, sorry, here's the point on the line. Here's a vector that's parallel to the line, and here's a third point, okay, that's not on the line. Okay, so let's have a look, and I can share my document camera with you again. All right, so the idea with this kind of problem, let me draw a picture first. All right, so let's draw a picture first. So here's a line, let's say, yeah? And I've got a point that is, let's say it's here. Okay? And what I would like to do is calculate that perpendicular distance. Okay, so it's a little line segment, and I don't know what the what P is, where it is, but that's sort of what I want to compute. Now, I do know a point on the line, and I do know a vector that is parallel to the line. Okay, so what's very common in these kinds of problems is you connect these 2 points, and then you have a right-angled triangle. Okay, so the idea is you want to compute that distance there, which is just the length of the vector BP. Okay, so how do you do it? Well, it's a right-angled triangle. Okay, so you can work out this distance. If you can work out that distance, then you can work out this distance. Okay, so how do we do it? Well, by Pythagoras, we know that this distance is just the following. Okay, so this is easy to calculate because I know this point and this point is given to me. This is a little bit harder. Okay, this, the vector AP is just the projection of this vector on the vector V. Okay, so this is one of those questions where you're using projection to calculate something, right? Okay, so what do we do? Well, this vector is just the projection of AB on V. Okay, and what is this? Well, it's just the dot product divided by the length and multiplied by a unit vector in the same direction as V. So this is a unit vector. It has length 1. It points in the same direction as V. And this is kind of like a signed length. Okay. So we don't really want the vector. All we want is its length. So I can take the following. The length of this is 1. And all I need to do is just take the absolute value of the top. Okay, so that's the idea behind it. let's do it with some numbers and we can actually solve this problem, okay? So let's see how we actually work these things out. I always like drawing pictures. It means I don't have to remember formula, which is kind of nice, right? Okay, so in our problem, A is the point 1, 2, -5. B is the point -2, 1, 5. And V is the vector 6, 3, -4. Okay, so this is just the information we're given for part A in the notes. All right, so what do we need? We need the vector AB. Okay, that's going to be an important calculation. So the vector AB is just the position vector of B minus the position vector of A. So -2 minus 1. 1 minus 2. And 5 minus -5. That's 10. Okay. And what else do we need? We need the length of V. So if that's V, let's find its length. So how do you compute the length of a vector? You square the components, add them together, and take the square root. So 36 plus 9 plus 16, and you take the square root. Okay. So what else do we need? We need this. So if that's my vector AB, what is the square of its length? Well, just square the components and add them together. So 100 plus 1 plus 9. Yep. And lastly, let's compute this. Okay, we really want the square of that, but this is okay for now. So in addition, this length here is going to be the dot product, absolute value divided by the length. So the length is root 61, so that can go on the bottom. And how do we compute a dot product? Well, you multiply the components together, the corresponding components. So -3 times 6 plus -1 times 3 plus 10 times -4. Okay, so this dot product is going to be just that. So -3 times 6 plus -1 times 3 plus 10 times -4. We're taking the absolute value. We're dividing by that, which is root 61. Now, believe it or not, this just gives you 61. Isn't that nice? So the square of this, which is what we need, is just going to be 61. Okay, so let's see what the important information here is. That's important. That's important. We're going to put this and this into here, and we'll get our solution for the length. So last part of the problem. Okay. So we're using Pythagoras' theorem there. It's going to be 110 minus 61 square root, which is 49. We get 7. Awesome. Awesome. Now, that's a long problem, and I spent a lot of time doing that, right? Because I wanted to explain it and solve it at the same time. Okay, now, you don't have to write all of this out when you solve these problems, but it's a good idea, to make sure you understand all the steps. Okay, questions, comments, hit me up in the chat, people. Hit me up in the chat. Okay. Let's go back to the PDF. All right. So that's a little bit about dot product and projections and minimum length. Okay. Let's have a look at another question. All right, Tom, what's going on? In the step where you find the dot product. Okay, let's discuss that, right? So I'll go back to my document camera. These are excellent questions. Thank you for asking them. So, okay, so I'll just go back to the picture. All right. So Tom's question is, in the step where you find the dot product, it didn't, why does it not matter what the length of the direction vector is? Are you talking about this one here, Tom? Yeah, this always has length 1. Okay, so we've done that in a very kind of strategic way. If you take any vector and you divide it by its length, that's you get a vector that has length 1. Okay, so for example, if I have this vector here, like what I mean by this is just 1 on the length times the vector. Okay, this doesn't really make sense, but this does. Okay, so if this is true, then if I want to find the length of this vector, then that's just this, and they cancel off. Okay? So what about the one to the left of that? Are you talking about this? So this, when you take the, like this could be positive or negative, yeah? So yeah, this could be positive or negative, and we don't actually want the vector AP, we just want its length. And so the length can't be negative. Does that make sense, Tom? So let's say the vector v was pointing in the other direction, okay? You'd still get the same answer, okay? Because it gets balanced between like with the dot product, okay? All you really want is the length there. Okay? So it doesn't really matter which direction v is pointing, if it's pointing that way or it's pointing the other way. It's still okay to use this approach when you're calculating calculating the length. So I hope that's helpful, buddy. All right. So hang on a sec, Tom. I'll come back to you. Omar, can you use the fact that the dot product of AP and AB is 0 to solve the question? I don't think so. I don't think so. Unless you know a way to do it like that. That's an interesting idea. Definitely V dotted with BP will be 0, right? So that's clear, because obviously if you move this up here, you've got to have a right angle. But I'm not 100% sure that you can use the dot product to get the fact that there's a right angle there. I don't think you can do that. But try it, Omar. Try it. Let me know. Have a go. Yeah, I agree. All right, Tom, back to your question. The parametric vector form, PVF. Yeah. So I love the PVF. Let me show you the PVF, and I can then move on to the next question. Okay, so an example of a PVF is parametric vector form. Hang on, sorry, I don't want to jump around too much. Aha, that's the parametric vector form right there. Can you see how there's a parameter, lambda, in it? Okay, and it's in a vector form. So that's PVF. This one down here is Cartesian. There's no parameter in this form. The lambda's been sort of eliminated. Okay, so this is PVF. This is Cartesian. Okay, I hope that's helpful. Okay, these are great questions. Keep the questions coming, people. I'm loving it. All right, let's get on to cross product. Now, sometimes when I discuss these kind of problems and we get to the cross product, the students, they get a bit angry because it's the cross product. So don't get too angry. Hopefully you can get excited about it. But it looks like regular multiplication, but it's not. And there's a definite procedure for calculating the cross product. But before we calculate the cross product, let's try to understand what it really means, okay? So here's a vector, oops. Here's another vector. What is the cross product of A and B? So let me go to GeoGebra. Did somebody say GeoGebra? I'll pull that up and I'll show you. All right. So here it is. Here's GeoGebra. I know there's a Desmos crew hiding somewhere, but this is GeoGebra. So here are the points associated with our vectors. Actually, I'll make it a bit bigger. Okay, in three-dimensional space. Okay, and let's put in the position vectors for those points. Okay, and now what I'm going to do, I'm going to put in the cross product. Now, what does it mean? What have I got there? Well, I've got a third vector, bit longer than the other two in this case, and it looks like there's some sort of relationship there. So I'm going to put in the plane that's spanned by the vector A and B. So it goes through the point A, the point B, and the origin. It is perpendicular. That cross product, that third vector, is perpendicular, normal to the plane. So this is a property with all cross products of non-zero vectors, right? And non-parallel vectors. If you cross them together, they give you a third vector that is perpendicular or normal to the plane spanned by the two vectors. Now, if I was to reverse the operation, instead of A cross B, you do B cross A, watch what happens. We get a fourth vector, and it's pointing in the opposite direction from the one we just calculated. So the order matters when you do it. Yeah, I know. We need some good music in the background, to really get on top of this. So order matters, and geometrically you get a third vector that is perpendicular, normal to this plane. Okay, so that's the idea. That's the idea. Now, Nabil, no confession necessary, right? I know Desmos is very, very popular. So let's have a look at these particular questions. So I'm just going to do the first one, do the cross product. Now, in lectures, you might have done this a certain way. So let me show you the way that I like to do it. It involves determinants. and you can make up your own mind. Okay, so here's one that I've sort of prepared earlier, and I'll share my screen with you. So I'll go back to my document camera, and we can have a look. Sorry, I know it takes a long time to share. I need some hotkeys or something to really go between different cameras. All right, so here's my first vector. Here's my second vector. This is 14a. What is the cross product of A cross B? All right, so the idea is going to involve a determinant. Now, determinants are something that you will see in the final section of this course when you do matrices, okay? So we define this notation to be A times D minus B times C. So you sort of work diagonally. Okay, so how do we do this? Well, the way I like to do it is to write it in this big form here where you have this sort of bigger determinant, 3 rows, 3 columns, and you write I, J, K vectors up the top. So let me know in the chat, is this something that looks familiar? Is this something that you've been looking at in lectures? Let me know. Does it look familiar? I know some people do it different ways. Some people just memorize the formula. You know, this is the way that I like to do it. Thank you for letting me know, everyone. So you start in the top left-hand corner, and you go to I, and then you play a game of cover up. I is in the first row and the first column. Cover up, and multiply that by the determinant of what's left. That times that minus that times that. Then move on to J. J's in the middle column, and the top row. Cover it up. Then multiply J by the determinant of what's left. Then move on to K. Cover K and multiply by the determinant of what's left. Okay? So this is the idea. Now, the only thing you need to be aware of is every time you move from column to column, you change the sign. So positive I, negative J, positive K. It seems a little bit weird when you do it like that, but there is a reason. Okay, there is a reason. So I've written it all out in terms of these 2x2 determinants, and you're just expanding along the top row. Okay, and now you go, okay, I times this minus that times that, and then that and that and that and that, that and that, that and that. Okay, that's the idea. So the first one is going to be 4 minus negative 12. All right, so it's 4 plus 12 times I. This one's going to be 0 minus negative 4. So that's going to become a plus 4 and you get a negative. Lastly, 0 minus 2 times 1. Okay, so a good question here is, Professor, why do I change the sign positive I, negative J, positive K? Does anybody know why we actually change the sign here? Because usually when I lecture this course, there's usually at least one student that goes, Professor, you have made a mistake here. Does anybody know why we go positive, negative, positive? Anyone? Smash that chat button if you know. It's okay. Thank you, Ning Xiao. Nabil, thank you. Okay, the reason is, right, if we want to use this 2x2 determinant, it has to match up. It has to be consistent with the formula for that horrible formula for the cross product. And so if we change the signs, then it works with this notation. So we're basically getting this determinant notation to work and fit with the horrible formula that you see for the cross product. That's the only reason why we go positive, negative, positive. Okay, so it works. Okay, hope that makes sense. All right, so you can write out the answer or as a column or IJKs, whatever. The important thing is you start with two vectors and you finish with another vector. Okay. Whereas with the dot product, you start with two vectors and you end up with a number. You don't get a vector as your number, as your answer. Okay, let's have a look, see if I can squish this one in here. I wanted to have a look at 16. Okay, so 16 is an interesting one, and I think that's definitely worthy of discussion. Okay, so prove the following properties of the cross products. So let me just do the first part, and we can sort of discuss these other ones. Maybe you can suggest how we do them. But with all of these problems, the idea is you start with the left-hand side. You start with the left-hand side, do some calculations, and then show that it's equal to the right-hand side. Okay, so the first part is very easy because you just want to work on the left-hand side and show that it's the zero vector. So let's try that. Okay. Okay, so this is now 16 part A. So consider, please, A crossed with itself. Okay. So the way I'm going to evaluate that is using the determinant method. Okay, and it's pretty easy, right? We just play our game of cover up like we were talking about before. So we sort of start up here and we expand along the top row. So let's start with I. I is in the first row and the first column, the top row. And then we multiply I by the determinant of what's left. So that times that minus that times that. You're going to get 0. What about J? That times that minus that times that. 0 again. And then K, that times that minus that times that. 0. So you're going to get 0I plus 0J plus 0K. Okay, so this is just the 0 vector. Okay, so that's not too difficult, right? It's very easy. Now, how would you do the other parts of this question? They're similar. You just need to work on the left-hand side of the equation and the right-hand side of the equation or the identity, and show that they're the same thing. Okay, so if I was to go, okay, what does that mean? We've already had a look at that in GeoGebra, right? We know that the order is important. That's one thing. So you'd work on the left-hand side and the right-hand side, no worries. Okay. And with this one, what does this mean? This means if you have a scale factor lambda, then you can bring that out, and the vector, the third vector that's the cross product, is scaled by that lambda as well. And this is something like, you can expand the brackets normally, like a distributive property. Okay. So I won't prove them, but yeah, I'll leave them for you to do. All right, Tom, if two vectors cross product equals 0, does that imply that they're the same? I don't think so. I don't think so. Let me have a look. Let me think about that. If they, I'm trying to think of a counterexample here, Tom, where you have two vectors and they're cross product and they're different, and they're not, and you don't get a zero answer. Maybe it's the only way. Oh, okay. No, I've got an idea. Okay, Tom, I think try these ones, right? What could you do here? What about? I'm just trying to think. So just give me a second. Okay, so just give me a second. See if you can find one, Tom. See if you can find a pair of vectors that give you a cross product to be 0, but they're not the same. See if you can do it. Okay. Yeah, same direction, probably a bit better. Yeah, 0 vector is good. Yep. So I think NASA is saying that if you take the cross product of any vector with the 0 vector, then you get the 0 vector. That's right, NASA, isn't it? That's what you're saying. So there's a counterexample for you, Tom. It's called the NASA counterexample. Okay, so that's better. I like it. So I guess the next question is, can you do it with two non-zero vectors? Okay. All right, let me continue. I want to do the scalar triple product. Okay, so I'm going to move on to 25. Okay, so here we now have a scalar triple product and volume, right? And so find the volumes of the following parallel pipets or parallel pipes. I call them parallel pipets. Okay, so one way to do this is to draw a little picture and then think about how it all works together. So I'm just going to draw a picture now. I'll go back to my document camera. And a lot of students, they can use this formula, but they're not quite sure why it works. So let's say I have a vector B, a vector C, and a vector A. All right, so together they can form a parallel pipette, right? That's a badly drawn one, but you get the idea, right? It's not a very good picture. Okay. All right, so they're like the three sides that are important. And the volume of this is given by this, what's called the scalar triple product, and you take the absolute value because you can't have a negative volume, right? So how does this actually work? Well, we know that the volume is the area of the base multiplied by the perpendicular height. Yeah? And so the area of the base is just, in this case, a parallelogram. So this is just that. And the perpendicular height, well, how do we compute that? Well, I'm glad you asked. If you have the cross product, oh, sorry, that should be B cross C. Okay, so you cross these two vectors together, you get a third vector that looks up like that. What you want is that distance there. That's just the projection of that on that, and you take the absolute value. So okay. So how do you work it out? Well, the projection of A on this is just the dot product of that divided by. Oh, that should be B cross C, sorry. Okay, it's the bottom two vectors. Okay. Okay, so bump. Okay. Technically I should have those the other way around, but it's the length, so it doesn't really matter. Okay, so that's where it comes from. Okay, so if you want to calculate Tom, the order matters. The order doesn't matter for the length, but it does if you're not worried about the length. Okay. The order doesn't matter for this either because we're taking the absolute value, right? So you can change the sides around. The order doesn't matter for the length. Okay, so in question 25, we're asked to compute the volume for parallel pipette. So let me just go back to the PDF. So here it is. Find the volume, and there's three vectors there, say A, B, and C. And so how do we do it? Well, let's just use the formula that we just derived. And here is the way that I've done it. Now, I've done it two ways here. I've gone, okay, here's A, B, and C, and you worry about this. So you've got a determinant in here, and you take the absolute value. So you expand along that top row like you would with cross product, okay? But actually, you can see down this side, I've done it a different way. I've actually put this up here, and that's going to simplify your calculations because you have a 0 there. So this first bit's going to be 0. Okay, so with these volume type of problems, you can simplify the calculations by just writing the scalar triple product and its absolute value in a certain way. Okay, it doesn't matter if you do this, you should get the same answer of 14 cubic units, but I just did it there to save some time. Okay. So to answer your question, Tom, for the cross product, it definitely matters. But if you're finding area or volume or length, then the order doesn't matter. Does that make sense, Tom? Good. So I'm usually pretty sensitive with the order, but with these kind of problems, the order doesn't matter, right? Because you're taking the absolute value or the length or whatever anyway. Oh, Crystal, great question. Does it matter which letter we allocate the vectors, as the question didn't do this? That is a good question. What do people think regarding Crystal's question? Does it matter? Yes or no? Does it matter? Nisa, Ningxiao, Liz, Isabella all say no. It's correct, right? It's correct. So it doesn't matter how you label it, Crystal. You should end up with the same answer. Yeah. Absolutely. So it doesn't matter. Yeah. It's a good question though, right? Because it's like, well, does it matter what I label, where? No, it doesn't matter. Okay, you're welcome. All right, folks, time to go. I'll see if I can start next week's tutorial with a little bit of C-pop or K-pop, or J-pop. I hope you're having a good week 4. And look, just good to see you again, everyone. Remember, the week 6 is not very far away, and at least you get a little bit of a break then. The last thing I wanted to say, the practice tests for lab test 1 are up. Good luck. Do the practice tests. That's the best advice. Okay, everyone. Bye. Thanks, everyone. See you.